Okay, so grugpool. I don't know if anyone wants to join in with the demo, but they can go to tinyurl.com/grugpool and it will take them to this kind of gist readme where we can run the pool and see and send some transactions from the pool and see how it all works. There's an easy mode, which is just the reg test demo that uses like a Docker image, which I'm going to show here. Run this script. One thing is the internet is kind of bad, so it might take a very long time to download the stuff. So all will be explained soon, but that's what the easy mode of the demo looks like. And then the hard mode is using Signet, but we need to download a Bitcoin Inquisition node, which has CTV and other opcodes available. So if anyone wants to try it out, then they can go to this URL and follow along. Okay, cool. I am Stu, or StuTXO, and this little cat, I guess. Not affiliated with Opcat in any way, but what is grugpool? So grugpool is an implementation of Jeremy Rubin's coin pool using CTV. So the characteristics of this coin pool are it's a single UTXO shared between multiple users. Every user can withdraw their funds without just unilaterally, without cooperating with anyone else. A set of users can then authorize spends in the pool, so they can collaborate, and if everyone collaborates, and they can do payments wherever they want. And then once the payments are made, the rest of the funds go back into a new pool. So I decided, I was kind of interested in CTV and learning Bitcoin script. So I was talking to Floppy and asking for some ideas of what I could do with CTV. And he mentioned that he made something, a payment pool using CTV, like a proof of concept, and he basically recommended that I give that a go. So this is quite a good tweet thread that he made about this payment pool. Okay, so why payment pools? Well, Super's net talk. So Super was going to be talking now, but we swapped it around because his talk is it's about payment pools as well. It's like the advanced version of this, so it makes sense that he's going to go next. So he'll be able to explain it much better than me. But they basically allow us to scale by sharing UTXOs, and they improve privacy because when someone leaves the pool or a payment leaves the pool, it's very hard to tell who made the payment. And obviously, if you always wanted to be part of something, then you can join a payment pool. Okay, so why grugpool? So grug brains is like development kind of term or philosophy where everything's very simple. So the eternal enemy of grug brain is complexity. So complexity bad, very bad, very, very bad. And the eternal enemy of grugpool would be pre-signed transaction. And the final boss of pre-signed transactions is AddXP. He's building Arc right now. Anytime anyone says anything, he's like, oh, pre-signed transaction. But they are amazing. Okay, they're really good. We have Lightning, we have Arc because of this. So some really exciting stuff. But it's just, for a grug brain developer like me, it's kind of like to get my head around how I can make this pool with pre-signed transactions and like having a coordinator and signing all these transactions and storing them and passing them around. It's it's just not grug brain enough for me. So I'm building this with CTV. CTV enables covenants. So what are covenants? It's very simple. They just let you set rules on where the coins can be transferred. So at the moment with Bitcoin script, if you have the keys to your address, keys to your wallet, you can just send to any Bitcoin address. But covenants, they only let you send to a certain predefined address, which turns out is very, very useful. And it also turns out that Gregory Maxwell came up with this, as all things in Bitcoin, in 2013. So yeah. Okay, so what is the problem we're trying to solve with covenants, CTV, and all this stuff? Well, this is what we don't want to happen. We don't want Bitcoin to be a custodian electronic asset system. We want it to be peer-to-peer digital cash. How do, I mean, I guess it kind of works right now, but it's not, Bitcoin is not very private, and self-custody does kind of suck for like everyone. My sister is not going to use a Bitcoin hardware wallet. It's very scary for these people, so this is what tends to happen now. People are going back to custodial solutions. Lightning's great, and all these exchange stuff is great, but Ben the Carman, he had a great talk at the last bitcoinconf in Austin about like how if we were to open Lightning channels for everyone, it would take like 6 years to do this. There's not enough block space, and the UTXO set would just balloon up. And, yeah, it's kind of a problem that we need to solve. Peter Todd also had a great article about covenants and scaling limits of Lightning. That's pretty good to read. But yeah, this is for me, I guess. Well, at the moment, the mempool is pretty empty. You know, you can get your transactions in for pretty cheap, but hopefully it's not going to be like that eventually. So we need to figure out what we're going to do. Okay, so when could covenants happen? I guess there's a lot of talk about it now. There's a few proposals. There's this hash collider thing where you can technically do covenants right now in Bitcoin, but it's very expensive. And there's all sorts of different proposals in the pipeline right now. There's a few clients that are trying to get activation, that may be rolling out for activation, so Enhance, which includes OpCTV. And this was a recent post about activating OpCTV, OpCat, and CSFS this year, apparently. So, yeah, good luck with that. Okay, and this is a fun channel to be in. It's just past week, there's been like a lot of spam, a lot of talk, and then Ryan Gentry popped up and just posted this meme. And it's pretty much what this guy's saying now, I guess. But it's kind of funny. Okay, and then there's obviously Covenant FUD. It's kind of hard to find Covenant FUD because it's pretty much just if you FUD covenants, then you're FUDing like pre-signed transactions, or I don't know. But one FUD that I hear is the government can lock your coins up. And then you can only spend to certain government approved addresses. But you can just do that with multi-sig anyway and pre-signed transactions, so maybe it's not that big of a concern. And this is what the government are doing anyway, so I don't know if they're going to care. But yeah, this is my little line about CTV FUD, especially CTV, because other covenant proposal you could do like recursive covenants, and maybe there's some dangers there that are valid. Yeah. Okay, so covenant use cases, DLCs, I like that as a use case for covenants because it makes it very simple to design DLCs without all these pre-signed transactions, coordination and stuff. Scaling, there's all these new layer 2s that are happening, ZK, whatever, and they can make Lightning better, vaults, self-custody, privacy, or interactivity, yeah, or point control. There's a lot of use cases. There's some more here, some examples. This is probably the best thread on covenants on Twitter. Just as you should check it out. It explains different use cases and why they're important. Okay, so what is a layer 2? I guess anything that lets you unilaterally exit from the layer 2. And this word is said like way too much, so this is my very funny unilateral exit joke that I'll tell you now. If I hear someone say unilateral exit one more time, I'm going to leave and no one can stop me. Yeah, heard a few laughs. Yeah, and then there's this website, Layer 2 Watch, which has all the supposed Bitcoin Layer 2s. And there's like 50 or I don't know, there's so many. But like all these apparently Layer 2s, but there's literally only one there's Layer 2 really, which is, well, right now anyway, which is Lightning. Because it actually lets you exit from the channel. Or back to the channel. Okay, so CTV, object template verify. It used to be known as obscure the bag, and then before that it was known as this, check output hash verify. It has a lot of lore, maybe by far the most lore out of all covenant proposals, which is cool. It's not a recursive covenant, so you can't do recursive shenanigans. And it has a interesting cult-like following right now, mainly based on the idea that Jeremy Rubin's name sounds like a Reuben sandwich. And this is a picture of the first time I actually had a Reuben sandwich because of CTV influence, I guess. Okay, so how do we make it? How does CTV work? How does it work? So I've got some Rust code here with a very simple example. The simplest example I could make of spending a CTV transaction. So first thing we need is to define the output that we're going to spend. So we have the value. So in CTV you have to say how much you want to spend and the address you want to spend it to. The anchor amount here, this is to do with fees, which I'll go into a bit more later. So the idea is if the only thing that could ever be spent out of this Bitcoin script is going to be the amount we would specify here and the address we specify here. Okay. And then we pass this output into our CTV hash function. So this is what we need to build the hash to include in our Bitcoin script for CTV. So we need the version number, block time, how many inputs there's going to be. The CTV in particular, for some reason, it's like using one input is a lot easier than doing any other input. So if you want more people into like a pool that's using CTV, the best way to do it is just to combine everyone's inputs into one. So there's just one input left for us to work with. So we need the sequence hash, sequences, how many outputs it's going to be, and this pushes the outputs. And then we hash the outputs. We have the input index, which is always going to be 0 because we only have one input. And then we hash it all together, and it gives us just a 32-bit hash. And then we use that in our CTV script builder. So this is all that I'm using in this pool. This is the only Bitcoin script that I have, and yeah, we push the hash, we push the slice that we just created from the transaction, and then we push opctv. Okay, so and then when we go to spend, it's going to look at this hash, and then it's going to look at all the attributes that we defined here in the actual transaction, and check it against the hash to see if it matches. And then if it does, it lets us spend to everyone. Okay, so we have the script, and then we want to use a taproot address. So this is how we would create the taproot address. So we pass through the CTV hash. We then just do for now with the internal key, I'm just using some random key because we don't care for like the demo. You could use a number only once or something like thing instead. And then we create the CTV script with the CTV hash that we did here, and we add it as a leaf to the taproot builder. So it lets us, if we want to do a script spend, it adds this script as a way to spend, and yeah, that's it. This returns taproot spend info, which is where we can get the address from. Okay, and And then when we want to spend, because there's no signatures involved here, there's nothing like that, so it's very simple to spend from just a CTV script. So we get the, I guess you could call this like the script, tab root spend info. We need that to know what scripts are in the address to spend. And then we, again, get the same output, the same hash, and we add it to our script version, and then we use the control, we add a control block, and then we push to the stack, we just push the script version and the control block, and then that's it. And I have an example somewhere, it might be easier to show. CTV. Let's go. Just pick one of those. So this is the witness. So we have the script version we pushed here, and the control block. And then this is the for soft fork reasons, CTV is known as op. It's going to be op, not for, if we get CTV. So that's why it says op, not for. Okay, and then fees. We're using anchor outputs for fees. The reason we do this is, let's say we have a vault using CTV, and then in a year's time I want to withdraw. It's kind of hard to predict what fees are going to be like in a year. And in CTV you have to specify, when you make a transaction you have to say, oh, I want to spend, we saw it here, but I want to spend this amount minus this fees. So you have to create this. If you wanted to predict, or I don't know, in a year's time, you'd have to set all sorts of different fees and make lots of pre-signed transactions, which is what we're trying to avoid. So you can use anchor outputs instead, which allow you to set the fee to 0, effectively. So there's no fee. When you spend anchor output, the anchor has to have minimum 240 sats. It sends to this weird looking address called TB1P fees. That's the Signet one. And then the idea is you create one transaction, the parent transaction. It sends to your destination and this fee address. And then you child parent replace, whatever it's called, acronyms in Bitcoin are annoying. Child pays for parent. Child pays for parent. The fee, the one that's been sent to this fee address, which lets anyone spend from, and then you can use this child transaction to set any fee that you want, which is pretty cool. Okay, and this is just an example of CTV but with cat instead. So if for whatever reason we got cat and not CTV, then you could technically do this exact pool design, but the transactions would be a lot more expensive, and the complexity of the script is just crazy. So yeah, effectively this, you see here, this where we're pushing 32 bytes here is the same as doing this here, but then everything else is, we're like building the transaction on the stack, and then doing all sorts of cat and schnorr tricks, which Andrew Polster came up with. Okay, so how do we actually build a pool with CTV? So this is an example of a 4-person pool. The idea is you get 4 people and they want to join the pool, so they all add their inputs to like a PSBT, and they pass them around, maybe on Nostr, and they all sign their input, and then they broadcast this input to the first address, like the first pool's address. And then when they're in the pool, in this first address, any of them can leave whenever they want, without talking to any of the other users. So this meets the requirements of a payment pool with unilateral exit. So here in this example, you have Alice, Bob, Charlie, Dave, I guess. Alice wants to leave the pool to predefined address that's in the CTV script. So she can leave the pool, but the only way she can leave is by also sending the Bitcoin back to a new pool, which is this. This is a brand new pool here without Alice. And then we continue to do that. So then, I can't remember who it was. I said Dave. Is it Dave? We say Dave. Oh, sorry, Bob left. So Bob left. Now it's just Charlie and Dave left. And then the very last one, because the only way to spend this now, there's no point putting Charlie back into a pool, is we just let both of them exit to their own address. So to actually build the pool, we have to do the reverse. We have to build the exit addresses, the exit pools first. We do that because, well, let me just explain this first. Okay, so first thing we do, we get the withdrawal addresses, which we're doing here, which is this A, B, C, D. In my code, I'm just kind of generating them because it's a proof of concept. We just generate a bunch of addresses, however many we want in the pool. And then we use those addresses to create the pool. So in each of these functions, first one, we're going to create the exit pool, which is these ones here. So with a pool of 4, there's however many exit addresses here. With a pool of like 20, there'll be like, you can imagine the combinations, there'll be a lot of different combinations that we need without the whole pool. So we create the exit one first. We do this because then the other pools are all going to use, it's like kind of like a Merkle tree, right? So you have the bottom one, then the next level are going to use the bottom addresses so that they know to withdraw to. But you need to create these ones first, or this level won't know what address to send to. And if any of these addresses slightly change, then the taproot address for everything else changes. So yeah, that's why we need to do the exit pool first, and then we iterate. I can show you here. So this is the reg test example here for a pool of 10. So you can see here it's going through the. It doesn't actually log it here, but it creates the exit transaction, exit pool addresses. Then we're going up upper levels. So then we create it for 3 users. So in our example here, it'll be this level here. So then we create all the pool addresses for when there's only 3 people left. So Alice, Bob, C, they'll get their own address. Alice, Bob, Dave get their own address. And then within that address is the scripts that let you spend to the next addresses without the person who left. Because if they were a person left was included, then obviously they can just take the Bitcoin again, kind of thing, and we don't want that. Okay. So create, yeah, and then the very last thing we do is create the entry address. The entry address is going to be slightly different because it includes everyone and it lets everyone spend. Okay. So we explain this. This is an example of us funding the pool. So you've got four users consolidate into one UTXO. So now they're sharing this UTXO. And I have in my code I have like a kind of some function to simulate the PSBT getting created and passed around to the users. So this is what it looks like when you spend from a pool. The cool thing is it kind of looks like any other transaction. The only thing that gives it away is the script. You can see it's using CTV, which is like, oh, okay. Why is it doing that? So you might be able to guess that it's a pull from that information. But there is a way to maybe solve that, which I'll go into later. So this is the first user exit in. As you can see, they're sending 10,000 sats minus the fee to send to themselves. This is the withdrawal address. And then they're depositing the rest of the balance back into a pool. Which then, so this pool here, this address, will only let the remaining users spend from the pool. And then we go down, you can see now it's only 20,000 get sent, and so on until the very last set of users are left, and then they exit both of them, the remaining funds. Okay, I did make a 21-person payment pool, which took 40 minutes to create. Very efficient, and it created what, I don't know, just for a 21-person pool. So this shows how this is very quick and easy for maybe up to 15 people. But if you're going to do more than that, it starts to get very inefficient. But yeah, I think there are a few things you can do to solve that, and I think Super Testnet's talk next will be interesting for that. Okay, so try it out. I don't know if anyone was following along or wants to try it out, but I'm going to do an example here on Signet, hopefully. So yeah, this is the URL. The problem with Signet is I have to give you some points. So if you wanted to join in, then you can just leave your address, and I can send you some points. Yeah, a little bit more about Signet. There's a nice Discord where you can beg for some coins. Various Signet websites, and there's this really cool proof of work script that you can run, which mints you mints you Signet coins, and it uses opcat, which is kind of interesting. And this guy, if you spam him, he'll send you some coins. Okay, alright, so let's do a demo. So I have my wallet here. Let's see. Alright, we've got 1 Bitcoin. I'm rich. This is my Signet node just running here. We had to run the so in the README there's a bit more information here, but we have to run Signet with this Inquisition node added, so we can relay, because Signet, not every node has all the opcodes enabled. It's just this Inquisition port, which includes all the CTV, all that fun. So that is running here, and so I've set all the environment variables, so my RPC, user and password, Signet wallet, and then this is obviously, see, this works. So we're going to do a pool for 10 people. You can change it to whatever size you want in the config. You just change this line of code here. But we'll do 10 for now because it's kind of cool. Alright, we'll see what happens. Let's see if we got enough Bitcoin to do this. Okay, so we funded, and there we go. Okay, cool. So what just happened? We funded our wallet. I mean, in a real life situation, you wouldn't have to do this step because you already have your wallet funded. So this is the mempool.space Signet. Signet's kind of busy right now, but it looks like we paid some okay fees to get included next. So this is me just funding these wallets. Like these are all, I guess, the users that we're gonna join the pool. And then okay, so it created all the addresses before we do anything. Create them all, and then created the scripts with the hashes that spent all these addresses and all the users. So this is kind of simulating the PSBT spend, and this is the transaction that funds the pool. So you can see here, this is kind of like this is just my code, like being bad for fee management, but you can ignore them. The one we care about is this consolidation UTXO. So it's spending all 10 users here. They're spending with the PSBT into the first taproot address. So they're sending all their Bitcoin to, so it'd be this one, with 10 people in it. And then what we do is we just spend in order. So because it's just a proof of concept, so in the code we just run like this function, and it just empties the pool just to show that it's possible. It empties the pool in order, so it does Alice, Bob, Carol, Danny, etc. And you can see it doing it here. So so that's the funding transaction, and then Alice is going to leave. So we have the parent transaction here. Okay, it's not found because we are waiting for this. This is kind of the annoying thing about Signet and Inquisition as well, is it takes a while for the transactions to relay around. It would be useful if this Signet was also running Inquisition, but it's not, so we might have to wait a while for them to show up. Because our last transaction is not. But we can come back to that. But effectively, it's just going to show what we saw previously, which is these kind of addresses, but it'll just be more big ones. So the first exit will be for it'll be 100,000 Bitcoin. So there'll be 90, well not big sats. So there'll be 90,000 that leave the pool, and then one person leaves. Yeah. And with the reg test example, you can maybe see it easier. Because we don't have to wait for blocks in the reg test. So I have this local, it's kind of cool Bitcoin Explorer. It's written in Rust, so it's blazingly fast, I guess. But yeah, it's just in the Docker file, so we can look up the transactions here. And you will notice that in the reg test version, we have all the parent and child transactions. The reason for that is we're using anchor outputs in the reg test version, because it's just that's the way it should work. Whereas in the Signet one, as I said before, with the relay and stuff around, it takes a while. And also with transaction v3, when you're using anchor outputs, you have to wait for the previous transaction to confirm. It needs one confirmation. And if we did that for like 10 spends, we'd have to wait a long time to see each one get spent. Okay, so yeah, that's pretty much how the pool works, how you can kind of test it. If this was a real implementation, it would look a lot different. You'd be able to pick like what stage of the pool you're at, and what you like. If it's you want to exit at a certain stage, and you'd be able to do that. The really cool thing about using CTV to do this is we just need the original addresses that we created. It's pretty much it's the only thing we need to just recreate the whole pool, which is kind of cool and differs to the kind of pre-signed transaction way. Because with that, if you lose the transactions, it's very difficult to recreate them. But with this, you could potentially figure out the state of the pool by the transactions that have been spent, and you can recreate the pool with just these addresses. Okay, so let's see what we've got now. Yeah, so why grugdev like CTV pool? Well, for me personally, it was very easy to build with CTV and to think about how to build with CTV, because you just got this one script to worry about. So the Bitcoin like script stuff, which is it's very difficult to kind of learn this like new weird language, stack-based language. Well, with this CTV script, I just have to, okay, I have that, I know how it works, it just sends to an address. And you can do like a lot of stuff with just that capability. You can build things and have your code like do the logic rather than the Bitcoin script. And you can build some pretty interesting things. And this pool, it took me maybe a week and a bit to just make this like demo. To do that with maybe pre-signed transactions or another opcode company, it might have taken a lot more time. So easier to back up, reproducible, which I mentioned already. And how can we make the pool work better? Because at the moment it's very simple. The only thing you can do is you can withdraw from the pool using the CTV spend, which on its own could be useful. for various things like congestion control. Like you could have exchanges, if the network is very busy, you could have an exchange kind of send out a congestion control transaction which allows all, like, I don't know, there's like 1,000 users that they want to withdraw from Coinbase, and they set all of the hashes for these people's addresses in the script. So whenever these people are ready to withdraw, or if they want to withdraw very quickly, they could spend high fees to get their transaction to their intended address, or they could wait till the fees are low. So that's one way you could potentially use this design, like if CTV was available now, very, very easily. And it's kind of okay for privacy, because you don't know, the only people that know who's spending out of the pool are the people who created the pool in the first place. And if you had maybe one coordinator do this, then it's even less of a privacy leak. So that's kind of an interesting use case. Yeah. So how can we actually make it like useful and better? So we can use usig. So in the I'll show you the script we have now. It's probably easier to show it. So yeah, as I said before, for the internal key, we're using this unspendable public key. But what we can do is we can use usig here and combine everyone's private keys. So it's like a huge multi-sig for all of the users. So if there's 4 people in the pool, we could use their like combined public-private key as the internal key, and then they'll be able to spend to anywhere they want if they all agree. So I guess the way it would work is maybe they'll be talking to each other over Nostr, and someone will be like, oh, I want to buy a coffee over here. So then they would contact the rest of the pool and say, hey, I want to make this transaction. So instead of using all the stuff we did before with CTV, instead they use the internal key to spend once they all agree. And then they also create a brand new pool with the new amounts, and the users, maybe if a user completely left, they take out that user, or they reduce the amount that user can spend out of the new pool. So they create that new pool, they send the Bitcoin to to buy the coffee, to make the payment, and then they all go back into this new pool that they created, all using the internal key. The cool thing is about that is on-chain, it just looks like a normal spend. So this is like the real benefits of this, is you can have 10 people in this address, and then you might never ever find out that they're using CTV at all. The CTV spends are more so for like if there's an emergency. If one of the 4 people don't want to communicate, or they left the pool or whatever, like you can't get hold of them, then you can just use the CTV spends that we have here, the example here, to exit the pool. So you're never going to lose your funds. Yeah, and then this was Jeremy in Telegram telling me how I can improve it, and I have no idea what he's talking about, but yeah. And then yeah, Super's talk is next, so he's going to talk about more of this stuff, so you should definitely stick around for that. Okay, are there any questions at all? So, go to Super first.
Just a comment, it's always great when you're go-to line for the website.
Nice. Yes.
We're bringing the mic around, Stu. We have to talk to the mic.
Oh.
We're bringing the mic around.
Okay, let's do it again.
There you go. I just said a comment. I said that I always think it's great when you're go-to line for the website.
Very good. I think this guy had a question.
You showed how a participant can exit, but how does regular payments in the pool work? Do they have to
So the way the code that I have now is it doesn't really do any kind of internal payments in the pool. It's just the basis of a payment pool that you can use to just leave. Like you can just leave the pool effectively. I mean, you could, if you're trying to pay a certain, you could all agree, oh, well, we want to pay this entity at some point, and then you can unwind the pool and then it will pay them. But what I have here is just the basis, and then what you're talking about, where you can like interactive payments out of the pool, that would need some kind of like USIG, internal key kind of stuff to do some more interactive payments, and then you could use that to not broadcast to the network. You could do off-chain stuff and like updates within the pool and updating the state, like just using the internal key spend, and then also you always have the option to exit with CTV if you want. Any other questions? Yeah, so there's no interactivity required at all between users to unilaterally exit. Everyone can just exit on their own. In fact, because we have no signatures, I don't know if this is how it would work in like a real implementation, but our script is literally just CTV. So anyone that has the descriptors for this pool, which would be the other participants, they can make you exit if they want. Because they have the information. They can only make you exit to your address, so it's not like you would lose your funds, but technically another person could just say, I want to empty the pool, and they could just spend everyone's Bitcoin. Yeah, hopefully that answers.
As first proposal, hashes and holes transaction, algorithms and everything. I think in Germany posted updated. I don't know how to call. I can call it btcplusplus because it pretty much allows you to specify which parts of the transaction you want to use as a template for the back.
Yeah, sorry.
Because from my understanding, you're using the whole CTV thing, right? Not the CTV that you choose.
Yeah, I'm just using the whole. Just the CTV original bit 119 implementation. Yeah.
So if you use the CTV plus then you're reducing interactivity necessary to this kind of hardware version of like how many hashes you need. If you use the updated version, the upgraded version, then you choose which parts of the transactions you want to hash in the template.
I think you might still need to create all of the same hashes, because you still need each leaf, like Taproot spend has to have its own hash, which is sending to the address. So then I'm not that familiar with the CTV++ kind of thing. It sounds kind of like, what is it, like TX hash? Is that what, yeah, TX hash? I don't know much about TX hash either, but I imagine it would help in some ways, but I don't think it would reduce the amount of like CTV hashes that we need. I think it might stay the same. Yeah. Okay. You done? Cool. All right. Thank you.